So what piece of information does the second derivative give us about the shape of a curve? Yes, good job, Dean. Good job, Mikael. It tells us if it's a happy face or a sad face. It gives us the curvature, also known as the concavity. And so the test that we learned yesterday that allowed us to figure out what the concavity was called the test for concavity. Today we're going to learn a test called the second derivative test. And again, I've said this before, knowing the names of these tests is important because oftentimes the questions are asked by just telling you, apply the second derivative test. So the second derivative test uses concavity to give us information about extrema, about maxima and minima of the function. Uses concavity to give info about local extrema. So let's just draw a maximum. Does the curve that I just drew have a maximum? Yes. What is the derivative at the place where that maximum occurs? You got it, Myrna. Good job. 0. So local max occurs when f prime is equal to 0. Now, on this curve that I just drew, what can I say about the second derivative? Positive? Is this thing sad or is it happy? Yeah, it's sad. And remember, sad goes with negativity. So this is sad, therefore the second derivative is negative. What if I were to change and draw something that had a place where f prime equals 0 and f double prime is positive? What would that look like? It's going to be happy for sure. It's going to be happy. And absolutely, so if it's happy, then that means that place where the derivative equals to 0 has to be a local min. So local min occurs when f prime is equal to 0. So what we can see here is that if the second derivative is positive and the thing is happy, then it's shaped something like this, and clearly the critical value will be a local minimum. Where if the thing is sad, then it looks something like this and it's rounded downwards, and clearly any critical value on the interval will be a local maximum. And this is what the second derivative test tells me. So first it says that if f prime of c is equal to 0, so I have a critical value where f prime equals to 0, and f double prime of that same c is greater than 0, then f of x has a local min at x equals c. And that's that second case where we said, hey, look, it's happy, therefore we have a min happening. And B says, if f prime of c is equal to 0 and f double prime of c is less than 0, then f of x has a local max at x equals c. And that's the first thing that we looked at there, where it's going to be sad, so that clearly must be a max there. Okay, the third thing the second derivative test tells us is that if f prime of c equals 0 and f double prime of c equals 0, then the second derivative test is inconclusive. Now we're going to have one last statement here that's not actually part of the second derivative test, but it's important to recognize. In each of these things, we had f prime of c equals to 0. So that's only half, 1/2 of our critical values. This tells us nothing about whether or not we have a max and min when f prime does not exist. So here we can also add that if f prime does not exist, the second derivative test does not apply. So how we're going to start this, we're going to do an example where we actually just look at all of the functions that we looked at yesterday. Let me know in the chat when you guys are ready to start this. Ooh, sorry. Four of you are ready. Let me know when you guys are ready. Okay, so we're going to use the three functions that we looked at yesterday because they're already in your notes and because we've already found the first and second derivatives for them. And so that way we can really focus on the test as opposed to the simplification of the second derivative. And then we'll do a few more problems. So let's start with this, with A. The first function that we looked at yesterday was f of x is equal to x cubed minus 12x plus 1. And we had f prime of x was equal to 3x squared minus 12. And f double prime of x was equal to 6x. Okay, so what the second derivative test is telling me to do is to go back and find my critical values, but only when f prime is equal to 0. So here we kind of have this step one, critical values, find critical values where f prime is equal to 0. So I'm taking f prime of x and setting it equal to 0. So I have 3x squared minus 12 equals to 0, which means 3x squared is equal to 12. I just add the 12 over to the other side. So I'm doing like plus 12, and then here I'm dividing by 3. So I get x squared is equal to 4. And if x squared equals 4, what x values does that give me? Plus or minus 4. So I get x is equal to plus or minus 4. So those are my two critical values where f prime equals 0. Oh, thank you. Plus or minus 2. My bad. Plus or minus 2. So then f prime does not exist. I'm just going to write this here so that it's really clear that with the second derivative test, I don't have to think about this. So here, I'm not even going to think about it. I'm just going to say this is not useful for the second derivative test. And then the second step here is to plug those values into f double prime. And apply the test. So we're looking at f double prime of negative 2, so that's 6 times negative 2, which is less than 0. And f double prime of positive 2 is 6 times positive 2, which is greater than 0. Okay, so less than 0, that means it's sad, which means that negative 2, is that a max or a min? It's a max, you got it. It's that value up there. And then at 2, it's concave up, so it's happy, which means we have a min. So then our third step here is going to be to plug in to the original function to find the y values. So we have a max at x is equal to negative 2. So I'm looking at f of negative 2, and I plug it into the original function. To get 17. So my max is at negative 2, 17. And then I have my min at positive 2. Which gives me a negative 15. Okay, are there any questions about what we just did here and how we applied the second derivative test? Very good. Okay, so I'm gonna actually take a second and go back to our notes from yesterday and look at what we determined yesterday about this function. So yesterday was November 10th, and the function in question was this one. And so what we saw, yeah, I'm gonna graph it in just a second for you. Yeah, so I wanna use this to do it. So what we saw is that between negative infinity and 0, this thing was concave down, so it was doing this. So it was kind of like this. And between 0 and infinity, it was like this. And what we determined right now is that on each of those intervals, we had a critical value. Well, on the first interval, because it was sad, that critical value had to be a max. And on the second interval, that critical value had to be a min. So I'm gonna actually go back and we're just gonna draw a rough graph of this because we are gearing up to hopefully be able to graph these things. So what we saw was that between negative infinity and 0, we have it like this, and between 0 and infinity, we have it looking like that. Well, so I don't know exactly what this thing looks like, but I now have this idea that I have this max at negative 217, and I have this min at 2, negative 15. So if I were to draw a graph of this thing, even though I don't actually know what it looks like, it's probably something like this, where the y value here is 17, and that's negative 2. And here this is 2, and the y value is negative 15. So we have our max and our min that show up. And we can see that it kind of has to look something like that. Does that make sense? And we're going to have a much more like structured method to eventually graph these things, but it is good to start getting an idea as to how this information shapes the graph. Okay, I'm gonna let you guys get that down, but I'm also gonna write our second function down while I'm at it. So f of x is equal to ln of x squared minus 4x plus 40. F prime of x was 2x minus 4 over x squared minus 4x plus 40. And f double prime of x was negative 2 times x minus 8 times x plus 4 over x squared minus 4x plus 40 squared. Okay, so this is from yesterday. This was our second function. Are you guys ready to move on? Do you have any questions about the first one there? Okay, so again, we're gonna follow our steps from before. I wanna know when f prime equals to 0 for my first step. So my first step is we're finding those critical values where f prime equals to 0. And so that is when 2x minus 4 is equal to 0. So then I get 2x is equal to 4 by adding 4 to both sides. And then I divide by 2 to get x equals 2. For the second derivative test, do I care about where this doesn't exist? No, don't care. So that means we can move on to our second step. I don't care about where it doesn't exist. So now I am just looking at here f double prime of 2. I want to know if f double prime of 2 is positive or negative. So here I have a negative, so 2 minus 8 is negative, 2 plus 4 is positive, and the denominator is always positive. So does this give me a positive value or a negative value? Are you sure? So I've got 2 negatives and 2 positives, so this is going to be positive. So this is greater than 0, which means it's happy, which means is this thing a min or a max? You got it, it's a min. So that is my min. And then in our third step, we now want to plug that into the original function to find the y value. So f of 2 is ln of 2 squared minus 8. So 2 squared is 4, my bad. So we'll just do that. 4 minus 8 plus 40, which is ln of 36. So here I have a min at 2 ln 36. And notice how with this test, I'm not going to conclude that there are no other local maxima or minima, because this is only looking at where f prime equals to 0. And can I have a max or a min potentially where f prime doesn't exist? I'm going to write that question out. Can I have a max or min when f prime does not exist? Think about it. Think about what that could look like. What are some things that could happen when f prime doesn't exist? Let's say it's continuous, but not differentiable. What are things that happen when it's continuous, but not differentiable? Cusps and corners, vertical tangent lines. Could I have a minimum or a maximum at a cusp or a corner? Are you sure? Let's look at this. Could I have something like that happening? Could I have like this happening? And look, I do have a max there. I do have a min there. So the answer to this question is yes, but the second derivative test will not tell me about these, right? So I'm finding some max and min from the second derivative test, but not all of them. Does that make sense? Okay, I'm just gonna write down the information that we had yesterday about this. We had negative infinity to negative, that's an 8, not an infinity, oops. Negative infinity to negative 4, then we had negative 4 to 8, and we had 8 to infinity. And then we had this was down, up, down. But the only critical value I have here, the only minimum that we found was right here. So I would imagine then, can this look like that? Is this going to look like that? is this a possibility for what this graph looks like? Okay, better question. Why is this not a possibility for what this graph could look like? This is definitely wrong. How do I know that? I'm gonna give you guys 1 minute to think about it. Think about what we just said in terms of f prime doesn't exist. Think about what it looks like when f prime equals 0. How many values did we find where f prime equals 0? This graph is not possible. Why? Because meaning you're thinking in the right way, yeah. Okay, so this graph right here is not possible. Why? So this graph is not possible. So some of you are starting to get there. What is the derivative right here and here? What is f prime right here? How many times did I get f prime was equal to 0? When I look back what I did with the second derivative test, how many times did f prime equal 0? Once. How many times does f prime equal 0 here? 2? You guys sure? 3. 3 times. This is wrong because we know that it only has that minimum when f prime equals 0. It turns out this graph actually looks more like this. So if I were to have another max or min, for sure it would have to be a cusp or a corner. Turns out I don't, and this graph looks something like this, where if I were to like stick this on the axis, sorry, that's the wrong place. My minimum occurs at 2 ln 36. So I stick this on the axis, that would be 2, and that would be ln 36. And I know that this can't turn over and go back down because of what we just said. And also just FYI, I know that there are no cusps or corners here, largely because of what we did yesterday. There are no places where f prime doesn't exist because x squared minus 4x plus 40 never equals to 0. Okay, let's look at the next one. The next one that we did yesterday was f prime. I'm sorry, not f prime, f was equal to 12e to the x minus e to the 2x. F prime was equal to 12e to the x minus 2e to the 2x. And if double prime is 12e to the x, actually we had simplified f double prime, so it was 4e to the x times 3 minus e to the x. So now we're looking at our first derivative for our first step here. And we want to set it equal to 0. So I have 12e to the x minus 2e to the 2x is equal to 0. And a great way to solve this is to simplify. We need to find the greatest common factor. And to do that, you guys need to... 1 moment, please. Okay, so we need a greatest common factor, and we need to use our E rule that we used yesterday. What's another way that I could write e to the 2x? We saw this yesterday. I don't know what that means, Mikhail. Oh, are you talking about the greatest common factor? 2 is indeed part of it, but it's not all of it. How can I rewrite e to the 2x? You got it, Dean. We said yesterday that that's the same thing as e to the x squared. So you have on your notes from yesterday all of the rules that you need to know to see that. So it turns out e to the x is also part of my greatest common factor. So I have 2e to the x, 6 minus e to the x is equal to 0. So then I have e to the x equals 0, 6 minus e to the x equals 0, which gives me e to the x is equal to 6. Does e to the x ever equal 0? No, good job, Gwen. Never. Now you might need to look in your notes from yesterday. How do I isolate x from e to the x? Ln e rule thing, ln on both sides, you got it. So what I end up here is with is x is equal to ln 6. I'm taking ln of both sides. So here I got one value. And I don't care about where f prime doesn't exist, so I move on to my second step here. And I'm doing f double prime of ln 6, and I have 4e to the ln 6 times 3 minus e to the ln 6. What does e to the ln 6 equal? Again, rules from yesterday and rules from when we were doing logarithmic differentiation. You got it, Gwen. 6. So this is 4 times 6 times 3 minus 6, and I can see that it is less than 0. So it's sad. So is this a max or a min? You got it. It's a max. So now for my step 3, I know that I have a max when x equals ln 6. So f of ln 6 is 12 e to the ln 6 minus e to the ln 6 squared. So kind of the same thing that we did here, I'm doing here. So I get that this is 12 times 6 minus 6 squared. So I have a max at ln 636. And that's my final answer here. Okay, and I'm not going to talk too much about this graph. I'm just going to briefly show you guys what it will look like, so you can kind of have some, so you kind of get used to seeing what the graphs look like. So this is from yesterday. We had 2 intervals of concavity, so negative infinity to ln 3, and then ln 3 to infinity, and it was concave up and concave down. And what we see here is that we only have that one max at ln 6, at ln 636. So this is going to look something like this. Give me a second. That is a max at ln 636. So we have something like that happening here. So it's like concave up, but it doesn't give me a minimum. So it's kind of just doing this. And again, like I said, I don't want you to stress too much about the graphs right now, because we are going to be having like a very specific steps that we follow to eventually get these graphs. So we would say that that is ln 6 and that is 36. Okay, so those are all of the functions we looked at yesterday. And so there we really just focused on applying the second derivative test. Now we're going to start from scratch and have to like take some derivatives, simplify them, that kind of stuff. Are there any questions about the second derivative test, about what we have done up until now? No? All right then. So we're going to start with this one where I have f of x is equal to x squared times x minus 4 cubed. Okay, so the first thing that we do is, in the previous questions, we'd already done it. So we're needing to find the first and second derivatives. So what rule do I need to find my first derivative here? You got it, the product rule. So I'm like, the derivative of the first times the second plus the first times the derivative of the second. And what is my GCF here? So x minus 4 squared is part of it, but not all of it. There's something else here. So I have x minus 4 squared. Do I have anything else that shows up on both sides? You got it. There's an x there. So this is actually x times x minus 4 squared. So this is equal to x times x minus 4 squared times 2 times x minus 4 is left over in the first term, plus x times 3 is left over in the second term. And now I expand and combine like terms. So I get x times x minus 4 squared. And I'm actually going to flip the order of these because it might help you to see the next question I'm going to ask a little bit better. So I have x minus 4 squared times x. Then this is 2x minus 8 plus 3x. So here I have 5x minus 8. And this derivative is a wonderful simplified form for finding when f prime equals 0. Is it the best form for finding the second derivative? No. What can I do to make this a better form for finding the second derivative? Right now I've got like a product rule with 3 things in there, and that's definitely not good. You got it, Yasmina. So I want to distribute the x to the inside, and that's going to give me a good first derivative for finding the second derivative. So this is a good form for finding second derivative. Because remember, we said less product rule, more power rule. Good. Okay, so now what rule do I need for my second derivative? Again, a product rule. So I'm going to have the derivative of the first times the second plus the first times the derivative of the second. And there's my second derivative. And now, because I'm only plugging in here, I don't have to simplify this. It actually sometimes helps, makes it easier to plug in if you simplify, but it's not necessary. So here, only plugging in. So not necessary to simplify, though simplification might make plugging in easier. Okay, so I'm not going to simplify. We don't have to. I'm going to go to my first step now that I have all my derivatives, and I want f prime equals 0. So f prime equals 0. And I'm going to go to my most factored form for that. So here I'm saying x minus 4 squared times x times 5x minus 8 is equal to 0. And this is going to give me 3 values. What are they? What 3 values does this give me? So 0 is one of them. You got it. Good job, Dean. Good job, Jenny. So it's going to give me a 4, a 0, and an 8 over 5. And I don't care about where this doesn't exist, so I only stick to these 3 values. And then I move on to my second step, where I plug all of these in to the second derivative. Oh, I should start with 0. I'm going to start with the smallest one. So I'm going to do f double prime of 0. And I get 2 times negative 4 times 0 plus negative 4 squared times negative 8. And that gives me a value that is less than 0. So is that a max or a min? Less than 0, remember that means it's sad. And it's useful to always draw those things. So if it's sad, you got it. It's going to be a max. And then we're going to do f double prime of 4. And here I end up with 0 plus 0, so that equals to 0. We'll come back to that in just a second. And then we're going to look at f double prime at 8 over 5. And this gives me 2, 8 over 5 minus 4. And then we have 8 over 5, minus 4 squared times 10 times 8 over 5 minus 8. And it turns out that this is greater than 0 if you plug into your calculator. So does that give me a min or a max? You got it, that's a min. Now, who remembers what the test said about when the second derivative resulted in 0? Do we need to go back up and look at it? You got it. It says inconclusive. So here, this is inconclusive. So if we go back and look at the test, C was f double prime equals 0 as well, then the second derivative test is inconclusive. So here, we didn't get anything for 4. Maybe it's a max, maybe it's a min, maybe it's neither. So we move on to our step 3, and we're only looking at the 2 values. So we have a max at x equals 0, and f of 0 is equal to 0. So my max is at 0, 0. And we have a min at x equals 8 over 5. And f of 8 over 5, I plugged this in for us, is negative 110,592 over 3,125. So this is my min. And there we did that question from start to finish. Okay, are there any questions about this? All right, then. We're going to move on to the next question. We'll call this B, and we're still applying the second derivative test. So here our f of x is equal to x minus 3 times the square root of x. I'm going to give you guys about a minute, maybe more than a minute. I'm going to give you guys about 3 minutes. Find me the first and second derivatives. I'm probably going to interrupt you before you're done, but this way I want to see you trying to do that simplification here. I'm going to write down what you guys have so far, what I'm seeing here. So f prime of x, I'm seeing that you guys have the square root of x, so x to the 1/2, plus x minus 3 times 1/2 x to the negative 1/2. What you should be doing now is trying to find a greatest common factor. What is the greatest common factor here? Nope, not quite. Remember, so if I'm looking at the left side and the right side, the only thing I have on the left side is that x to the 1/2. So that's x. You guys got it, good. So there's also an x over here on the right side. The lowest power is negative 1/2. So that means my GCF is x to the negative 1/2. So I'm going to factor that out, x to the negative 1/2. What's left in my first term? In my first term, not 1/2. Not at, yes, exactly, x, you got it. So my first term is x, because remember what we've been talking about, I have 1/2 x's and I take away negative 1/2 of them. And that gives me my new power of 1. Good job, Yasmina. So then in the second term, I didn't take away the x minus 3, and I didn't take away the 1/2, but I did take away all of the x's. So this is x to the negative 1/2 times x plus 1/2 x minus 3 over 2. Is it okay to have negative exponents in my final answer? No. So what do I do with that x to the negative 1/2? What do I do with it? I bring it down. You got it. Okay. So I'm going to have 3 over 2x minus 3 over 2 all over x to the 1/2. And this is my first derivative. So this is my simplified first derivative. I could also write this like this, and it would be the same thing. And either of these is a good form for finding critical values. Is it the best form for finding the second derivative? Do I have a quotient rule right now? Can I get rid of that quotient rule? Remember we said when you have that one term on the bottom, you can separate. So this is 3 over 2x over x to the 1/2 minus 3 over 2 over x to the 1/2, which gives me 3 over 2 x to the 1/2 minus 3 over 2x to the negative 1/2. And this is a better form for finding the second derivative. And this is one of the things that you guys largely messed up on your group work. I saw a lot of people doing this thing that I said, never, ever, ever do this, and asking me, why is this question so long? And you took up like 2 whole pages trying to do it. And really, it should have taken 2 lines if you had separated. Okay, so now it's going to be super easy, just 2 simple power rules to find my second derivative. So f double prime of x is equal to 3 over 4 x to the negative 1/2 plus 3 over 4 x to the negative 3 over 2. And since I'm not setting this equal to 0, it's okay for me to leave it like this. I don't have to worry about simplifying or anything like that. So then we want to start by setting f prime equal to 0. We know that we only care about the numerator. So I'm going to keep it like this since I imagine this is where most of you guys would end up. 3 over 2x minus 3 over 2 is equal to 0. So that gives me 3 over 2x is equal to 3 over 2. And then I can just divide by 3 over 2, which is the same thing as multiplication by 2/3 to get x equals 1. Do I care about the value where f prime does not exist? I'm going to write it because there actually is one here. F prime does not exist. This happens when x is equal to 0. And we're just going to cross it out to be like, hey, look, we thought about it and then we remembered we didn't have to. Not useful for second derivative test. Now I just do f double prime of 1. And here I get that's 3 over 4 times 1 plus 3 over 4 times 1, which is positive. So this thing is happy. Do I have a max or a min here? I got a min, you got it. So that means my step 3 tells me that we have a min at x is equal to 1, and we plug that in. We get f of 1 is equal to 1 minus 3 times the square root of 1, which is negative 2. So my min is at 1, negative 2. Next, y'all ready? I was hoping to do 2 more, but it looks like I'm only gonna have time for 1 more. Let me know in the chat when you guys are ready. Or if you have any questions about the last one, you might start noticing that like this negative exponent thing is a thing. Like you're really having to deal with those negative fractional exponents. Okay, so let's take the first derivative. F prime of x is equal to 1 plus 1/2 x squared minus 6 to the negative 1/2. Hello. Is it all just gone? This seems bad. Give me a second. It's, hang on. It can't be gone, right? Everything that we just wrote down. Okay, all right, there we go. It's just having some issues. Okay, so taking our derivative, I bring my 1/2 down, x squared minus 6 to the negative 1/2, and then times 2x. Does this thing have a greatest common factor? No. So there's really not much I can do in terms of simplification, except I can cancel out those 2's because 1/2 times 2 is 1. And do I have a negative exponent? Yes, and we want to get rid of negative exponents. So here we'll say this is 1 plus x over x squared minus 6 to the positive 1/2. Good, okay. So now this is the only form that we have. Like, I mean, this is the best form. We're gonna have to simplify from here, and we're gonna have to find f double prime from here. By simplify, I mean we're gonna have to find our critical values from here and find f double prime from here. So f double prime of x is 0 plus, and now I have a quotient rule. So I have 1 times x squared minus 6 to the 1/2 minus x times 1/2 x squared minus 6 to the negative 1/2 times 2x all over x squared minus 6. And again, I don't have to simplify this, but I'm just going to take a second to make it a little bit prettier. So this is x squared minus 6 to the 1/2 minus x squared times x squared minus 6 to the negative 1/2 over x squared minus 6. And this brings us to our first step, which is setting f prime equal to 0. And I have a feeling that our critical value here might actually end up being kind of gross, but so how do I solve this? So here I would say 1 plus x over x squared minus 6 to the 1/2 is equal to 0. Okay, so now I'm going to take that 1 and bring it to the other side. So I'm going to have x over x squared minus 6 to the 1/2 is equal to negative 1. So I've just subtracted 1 from both sides. And now I'm going to multiply that x squared minus 6 to the 1/2 over. So what I have then is x is equal to negative x squared minus 6 to the 1/2. Okay, so something interesting has just happened here, and I want to know if you guys see it. I'm actually going to take a second, and this might help. I'm going to move this negative to the other side. So I'm going to divide both sides by negative 1. And that's going to give me x squared minus 6 to the 1/2 is equal to negative x. And if you don't see it, that's actually maybe better because it won't confuse you later. That's fine. So a lot of times people get confused here because we have this negative, and a square root can't be equal to a negative number. But don't worry about that if you don't see it, because it's not actually a problem, because x itself can be negative. So then my next question is, what do I do from here? How do I deal with the fact that I have a square root on the left side? If I have like the square root of x is equal to 5, what can I do? So we've talked about how we deal with those powers before. You got it, 5 squared. So here I'm going to square both sides to get rid of that 1/2. So I'm squaring both sides, and I get that x squared minus 6 is equal to x squared. Now what happens? What happens if I subtract x squared from both sides? What do I end up with? I get -6 is equal to 0. You got it, it doesn't exist. And sometimes that's going to happen. The x is just gone, and I ended up with something that's not true. And this can happen, and does happen. So in this case, we say that there are no critical values. So here, or rather, there are no critical values where f prime equals to 0. We can say f prime never equals 0. So is there anywhere to apply the second derivative test here? No. So f prime never equals 0. So we can just conclude then, similar to what we did when we had the extreme value theorem and the extreme value theorem didn't apply, we concluded that the extreme value theorem does not apply. The second derivative test does not apply to this problem. Okay, and next class, we're gonna do one more of these because I wanted to do one more today where I didn't want to end on an impossibility. I wanted to have at least one after the impossibility. So we're gonna do one more, and then we're gonna sketch our first curve by combining the increasing, decreasing, and the concavity, and like the max and min stuff. Are there any questions? Awesome. All right then, guys, I will see you tomorrow. Be excited, we're gonna sketch a curve. It's gonna be so fun.